We are talking chapter 14 last time, and we got into some talks about sort of phase changes and what happens in terms of sort of energy as we do that when we change the phase. Spit that out. So remember last time we sort of looked at the idea of as we go from, say, solid to liquid or liquid to solid. Again, as we talked about, this happens at the normal melting point, freezing point for a substance. Happens at the same temperature. It just kind of depends on energy, which way you're going. But there is a certain amount of energy required just to simply do that phase change. So, for example, like we talked about, if we had ice at 0 degrees and we wanted to take it to liquid water at 0 degrees, again, 0 degrees being the normal freezing point and melting point there of water. To do that, we would need what is known as the heat of fusion. And the heat of fusion, sometimes abbreviated with that change in enthalpy number, value, or symbol, delta H of fusion. And for example, for water, it's approximately 335 kilojoules, or sorry, joules per gram. And that's the amount of energy required just to do that. It works in both directions. It's the same amount of energy for water, regardless if you're going from solid to liquid or liquid back to solid. Just the sign changes. So as we talked about in the energy chapter, remember that if we have a negative sign for an energy value, that's an exothermic process. Energy is released. And if we have a positive sign, it's a endothermic process. Energy is absorbed. So as we go from solid to liquid, that's an endothermic process. It would be positive 335 joules per gram. If you go the other way, liquid back to solid, it would be negative 335 joules per gram. This is also sometimes given as 6.02 kilojoules per mole for water. And again, that's more of a kilojoule per mole sort of conversion. Same thing we talked about when we were talking about transition of going from liquid to gas or gas back to liquid. This happens at the normal boiling point for a substance. And again, it takes the same amount of energy going in either direction. Just the sign is going to be different. And once again, for water, that is what is known as the heat of vaporization, or the delta H of vaporization. And for water, that's roughly 2260 joules per gram, or about 40.7 kilojoules per mole, give or take. And again, it's going to be a positive value heading in this direction, going from liquid to gas, and a negative value, energy has to be released as it goes in the opposite direction. By the way, as we talked about last time as well, when we look at these numbers like the 2260 and the 6.02 and all that kind of stuff, that is specific for water. If you're dealing with some other substance, they will have a different delta H of fusion and delta H of vaporization depending on what the substance is. And additionally, they will also have a different, say, freezing point and boiling point as well. So, when we talk about kind of 0 and 100, that's specifically for water. And these numbers are specifically for water. And once again, if you're dealing with something else, they will have the same sort of values, but they will be different numbers if it's a different substance than water. We kind of tied this into like a heating and cooling curve that we saw. And remember that when we kind of do that, and I think this is ice down here, and this was like liquid water, and then this was like your steam, which is gas, and that was approximately 100 degrees, and that was there, 0 degrees Celsius. And remember that we can put all these sort of things together with what we learned earlier, which is the specific heat equation, the Q is equal to ms delta T. So remember that we use the specific heat whenever we're in the same phase, but the substance changes temperature. And again, we use something like the heat of fusion or heat of vaporization whenever we are at the same temperature but change the phase of a substance. So as we kind of went up and down this kind of cooling curve, and we did a calculation last time, pretty much anywhere where it's kind of going upwards, these guys are in the blue here are all in the same phase, and they're just changing temperature. So really anywhere in that blue, again, you would use the specific heat equation to do the calculation. Once again here, anywhere kind of in The yellow, where we flatline, that's going to be the heat of fusion or the heat of vaporization is used in that sort of calculation. As we also talked about, as you can see with the numbers, it takes a lot more energy to do the transition from liquid to gas than it does from solid to liquid, again, because as you go from liquid to gas, everybody's completely breaking apart from one another. So it takes a lot more energy to get everybody away from each other. As you go from solid to liquid, they're still relatively close to one another. So again, it doesn't take as much energy. So that's why when we look at this plateau, which means that they are not changing temperature here, we do see a much bigger sort of plateau line there for our transition of going from liquid to gas and backwards. Any questions on any of that we talked about last time there? Obviously, as we did a calculation, you could do these kind of in parts, the transitions as you're moving up or down. And at the end, you could add up all the energy for each of those steps, and that gives you the total amount of energy to do that transition. All right, then let us continue on here in this chapter. Next thing we're going to talk about are sort of forces within the molecule. More specifically, we're going to talk about forces between two different molecules. So the first type of force we're going to talk about is intramolecular forces. And intramolecular forces are the forces that hold pretty much like one molecule together, so one compound basically together. And that's basically like your bonds, so covalent bonding, ionic bonding, those are intramolecular forces. So if you had just one single water molecule, when we talk about intramolecular forces, those are the covalent bonds that we see here between the hydrogen and the oxygen. That's within the molecule. That basically holds that entire single water molecule together. Now, intramolecular forces, again, hold individual sort of compounds together or molecules. Again, ionic bonding is held together by electrostatic attraction, which is an intramolecular force as well. Very strong sort of forces. So these are really strong forces because otherwise, if they were weak forces, everybody would just fall apart and make alphabet soup and all the letters and elements would come apart. But here it holds the molecule together. Now, that is different than intermolecular forces. Intermolecular forces are the forces that hold one entire molecule together with another. So if you had not one water molecule, but you had two water molecules or multiples, because water is a polar compound, what that essentially means is it has, as we talked about in bonding, unequal distribution of electrons overall. And what it creates is a positive side to that molecule and a negative side to that molecule. So on water, hydrogen is more positive and oxygen is more negative on water molecules. So where the hydrogens are is more positive and where the oxygen is more negative. And what that allows is a interaction between this entire water molecule and this entire water molecule. They basically can interact with each other through the positive side of one and the negative side of another. All intermolecular forces basically react through that interaction. Pretty much all intermolecular forces are the positive side of one molecule attracted to the negative side of another. So opposites attract. And that's what holds together multiple water molecules together through this. And as we'll talk about here, this is what is referred to as hydrogen bonding. That's an intermolecular force. Now, we know, for example, as I mentioned a second ago, that intramolecular forces, which are the individual bonds between the oxygen and the hydrogens in each molecule, are much stronger than an intermolecular force. And we know this by water is a very good example of that. When we heat water up, the bond that breaks first is this bond right here between the two different water molecules. So when we heat up something like water, we get steam, and that's water molecules basically going off into the gas phase if you heat it up. Now, if it was opposite and the intramolecular forces were weaker, what would happen is as you go to heat these water molecules, these bonds would break and you would start making hydrogen gas and oxygen gas, which obviously we know from heating water does not occur, and everybody would fall apart. So intramolecular forces are always much, much stronger than an intermolecular force. And again, the strength of that intermolecular force, as we'll talk about, is basically what gives things certain properties, things having high melting points or boiling points or lower melting points or boiling points. So the stronger this bond is between molecules, the most likely it will not exist as a gas under normal conditions. The weaker that bond is, most likely it's going to fall apart a lot easier and allow them to go off into like the gas phase a lot easier, and you would have more of a gas at normal temperatures and conditions. So what we're going to talk about here are intermolecular forces mostly, and we're going to talk about some different types of intermolecular forces. And again, these are the forces between one molecule and another. The first type of intermolecular force is what is referred to as a dipole-dipole interaction. And if you remember, dipole came about when we talked about bonding and polar molecules. Remember that a polar molecule has what is known as a dipole moment, right? So a dipole moment is what polar molecules have. That is represented by that like arrow that looks like this, if you remember from bonding. And remember that a polar molecule as a whole will have a dipole moment where, again, this arrow kind of points to the more negative side of the molecule, and the back part here is the more positive side of the molecule in this case. So dipole-dipole interaction is an interaction between basically two polar molecules. So if you have a polar molecule, again, there's going to be this distribution of charge. So you will have a positive side and a negative side with a polar molecule. And you will have another polar molecule that has a positive side and a negative side. And it is through the negative side of one molecule and the positive side of another that they're able to interact with each other and bind. And that is what is known as dipole-dipole interaction. This is the major type of interaction that occurs between polar molecules and polar molecules. As a side note, we'll talk more about it in a second, that cannot hydrogen bond. So these are polar molecules that cannot hydrogen bond. They typically will use dipole-dipole interaction as their main source of interaction between two polar molecules. It is only, again, about 1% as strong as covalent and ionic bonds. And again, covalent and ionic bonds are more intramolecular forces, as we talked about. Again, there's really stronger forces.
Bonds between atoms with different electronegativities have a permanent dipole, that is, a separation of charges, because of the unequal sharing of electrons. Some molecules which contain polar bonds do not have a net dipole. For example, carbon tetrachloride has polar carbon-chloride bonds, but the polarities cancel as a result of its symmetrical structure. It is therefore a nonpolar molecule. Even though the chloroform molecule has a tetrahedral shape, one of the outer atoms is different from the others, so the molecule is not symmetrical. This means the bond dipoles do not cancel, and the molecule has an overall dipole moment. It is polar. Molecules such as sulfur dioxide have asymmetrical structures due to one or more unshared pairs of electrons on the central atom. Sulfur dioxide is an asymmetrical molecule with polar bonds, therefore it is a polar molecule. When polar molecules, such as sulfur dioxide, are close to one another, they tend to align so that the positive end of one molecule points towards the negative end of another molecule. Attractions among polar molecules are called dipole-dipole forces.
So again, the attraction there again is always between sort of the positive side of one and negative side of another. This is a relatively strong intermolecular force because polar molecules, no matter what you do to them, will always have a positive side and a negative side because of that unequal distribution of electrons, which means essentially they're good to go. They're like ready to do this interaction. They don't have to wait for anything to happen. They have a positive side, they have a negative side. This is how polar molecules interact with themselves, other different polar molecules as well. And again, what happens is as they come together, there's always going to be a chance for sort of a positive side of a molecule to be next to another positive side or a negative next to a negative. So they do try to move around to find the best arrangement that maximizes the attraction forces between the positive side of one molecule and the negative side of another and minimize kind of similar charges being near each other, which is what happens here. They'll kind of keep moving around until they kind of find a acceptable spot. Another type of dipole-dipole interaction, which is actually a really strong interaction, is known as hydrogen bonding. And hydrogen bonding is a special type of dipole-dipole interaction. In order for something to have the ability to hydrogen bond, it needs to have a hydrogen that is directly attached to either nitrogen, oxygen, or fluorine. And if you look at the periodic table, that is the upper right, nitrogen, oxygen, and fluorine. That is the upper right of electronegativity values. And when that happens, that means hydrogen is going to be attached to something that's going to make a really polar bond and a really separation of charge of positive and negative that's here. And that is what is known as hydrogen bonding. And that is exactly what happens when a water molecule and another water molecule come together. Again, this is going to be positive, it's going to be negative, the oxygen, and they're able to hydrogen bond here. Each of these guys can hydrogen bond because the hydrogen in this case is directly attached to an oxygen, a nitrogen, or a fluorine. Same thing on this guy could also. This also is a really important sort of interaction because it allows certain other types of molecules that have a similar bond to be able to interact well with water. So, for example, if you took something like methanol, which looks something like this, and you take something like water, water again being more negative, hydrogen being more positive. Now, when we look at this part of methanol, these are all nonpolar bonds. But it does have this bond over here, which is definitely polar, and that is going to create the negative on the oxygen and positive on the hydrogen because of that. And that's going to allow this guy to hydrogen bond with water. And that's going to make actually something like methanol soluble in water because it has the ability to hydrogen bond with it. Now, again, it's able to hydrogen bond because our hydrogen here is directly attached to an oxygen. So it's able to do the hydrogen bond. Now, when you look at something like this over here, this part of it, you may be asking, can we hydrogen bond with any of these? And the answer is no, you cannot, because those hydrogens are not directly bound to a nitrogen, oxygen, or fluorine. So just having a hydrogen present doesn't allow it to hydrogen bond. It needs to be attached to nitrogen, oxygen, or fluorine to have the ability to make that polar bond that is necessary for the hydrogen bonding to occur. So if you had something like methane, once again, it has a ton of hydrogens, but none of these hydrogens can hydrogen bond. So none of those can hydrogen bond because, again, they're not attached to the right thing. They're actually all non-polar bonds, which means there is no separation of charge because electrons are being shared equally. So in a non-polar bond or molecule, there is no positive side or negative side, so it's lacking that necessity of having the positive or negative present. Any questions on that? Also, why something like NH3? NH3 can hydrogen bond. Again, it has a hydrogen that is directly attached to a nitrogen, and it is a polar molecule, so it definitely has the ability to hydrogen bond in this case, and would be able to do so. So hydrogen bonding is a special class of dipole-dipole interaction. It is considered to be stronger than dipole-dipole by itself. And that's what I said a second ago, that with dipole-dipole interaction, it is for polar molecules that cannot hydrogen bond. So if you had a polar molecule, like in the example that we saw there, which was, I think, something like this. I could be wrong, but it was something like this guy with a hydrogen. So this guy here would do dipole-dipole and not hydrogen bonding because, again, even though it has a hydrogen, that is not one that can hydrogen bond. So the best that it could do is just dipole-dipole interaction. So for any polar molecule that does not have that ability to hydrogen bond, it's going to roll with dipole-dipole interaction as its main interaction. Some polar molecule, like for hydrogen bonding, is between polar molecules and polar molecules that can hydrogen bond. Pretty much, because in most cases, I would say, I'll put it this way. Probably if you have a hydrogen that's attached to nitrogen oxide or fluorine, it's going to be perhaps a polar molecule, but it will definitely have the polar bond. So it needs that polar bond. So technically speaking, a lot of organic compounds like what we have here with like methanol, they kind of have like two parts to it, like a non-polar part and a polar part. So it does need like a polar part with a hydrogen that's attached to one of those to be able to do so. So like this entire molecule here is technically slightly polar because of that bond, but it does have a non-polar part. So usually polarity will help out with that being able to hydrogen bond. Other questions?
Some polar molecules have unusually strong intermolecular attractions called hydrogen bonding. These attractions occur in molecules where hydrogen is bonded to fluorine, oxygen, or nitrogen. The interaction occurs between the hydrogen of one molecule and an unshared electron pair on the more electronegative element in another molecule. The orientation of hydrogen fluoride and water molecules in the liquid states of these substances is determined by hydrogen bonding. The hydrogen atom in hydrogen fluoride is attracted to the fluorine atom on another hydrogen fluoride molecule. Water, with two hydrogen atoms and two unshared pairs of electrons, can form 4 hydrogen bonds per molecule. In ice, hydrogen bonding leads to a tetrahedral arrangement of water molecules around one another, forming 6-membered rings that leave open channels through the ice structure. In liquid water, the tetrahedral arrangement is not fixed because the molecules are able to move around, and on average, a water molecule is surrounded by 3.4 other water molecules. Hydrogen bonding forces are unusually strong attractions that occur among molecules in which hydrogen is bonded to a highly electronegative atom.
So as we just saw there, back it up again, I think. Here, maybe.
Some polar molecules have unusually strong intermolecular attractions called water molecules around.
So earlier in this chapter as well, we talked about ice having less density or is less dense than liquid water. And this is the reason why through this hydrogen bonding, as you can see in this picture, this animation, there's all those big open sort of spots between the water molecules. Again, as we talked about earlier in this chapter, if you just think about the density formula, which is mass divided by volume, all that open space, that empty space between all those water molecules, again, is going to kind of bloat his volume and make his density less because of this really strong hydrogen bonding that occurs. And also, when it goes into the ice phase, it doesn't have as much energy, so they can't get as close as they can. Like you see here, as it continues in the water, you can see it kind of collapse.
Channels. Structure. In liquid water,
And again, here in liquid water, as you can see, those big open spaces are not as prevalent there as you see in the solid stage. And again, the volume doesn't get as bloated. And that's why, again, an unusual property of water is that fact that we talked about earlier, that in the liquid state, it has a higher density than in the solid state. And it's because of this really strong hydrogen bonding that occurs and the lack of energy to kind of get everybody closer to one another. Any questions on that there? And again, here's our hydrogen bonding that's happening. Now, another type of intermolecular force is what is known as dispersion forces, sometimes called London dispersion forces. And these are relatively weak intermolecular forces. These are like the weakest you could have type of intermolecular force. And this is the main interaction that nonpolar molecules and nonpolar molecules use. So this is the main sort of interaction between two nonpolar molecules. It's the dispersion forces. So there's a couple ways that this can occur. There is what is sometimes referred to as a dipole induced dipole interaction or an ion induced dipole. And what that means is, for example, if you had a nonpolar molecule, it is basically going to be neutral. There is no positive side, there's no negative side to it. It's just kind of like a neutral sort of molecule. And what happens is if you kind of roll a polar molecule next to it, it will have a charge, obviously, that polar molecule. And with the polar molecule being next to it, what's going to happen with the electrons in the nonpolar molecule is it's going to go, oh, I don't want to be near that negative side. So they're going to go away from that negative side. And what's going to happen in this case is that polar molecule will now kind of induce or create a temporarily charge separation in the nonpolar molecule. So this nonpolar molecule that normally does not have any type of separation of charge, because you rolled up a polar molecule, or even an ion can do this as well, next to it, it will be able to temporarily get that interaction between those two molecules and interact with one another. It's temporary because as soon as this guy kind of rolls away, this charge is going to kind of go away as well. So it is not a fixed charge. It's kind of a temporary attraction. It will go away. It is, for example, similar to, again, oil and vinegar salad dressing or something like that, right? If you mix it, it stays mixed for a while, right? Because they're able to kind of interact. But eventually they will separate out because they cannot maintain that interaction over the long period of time. And they won't be able to do that with oil being nonpolar and like vinegar being kind of polar. They won't be able to maintain that interaction. Everything, polar molecules, nonpolar molecules, can sort of do dispersion forces, but really it is not the main type of force that polar molecules use. They use either dipole-dipole or hydrogen bonding. This is specifically the only force that nonpolar molecules can use. So this is what is referred to as, again, a dipole-induced dipole, what I kind of diagrammed there. The other way it happens is what is sometimes referred to as an instantaneous dipole. And what that is actually just two nonpolar molecules, for example, that are going to be kind of neutral. And because electrons are flying around in the molecule, it is possible that the electrons could all end up kind of on the same side of the molecule temporarily. So if all the electrons in this guy decided to all fly on vacation over here, what's going to happen is temporarily that nonpolar molecule on the left-hand side will now create a separation of charge temporarily because the electrons went one way. And if he is still next to our nonpolar molecule, that's going to cause the electrons in this guy to also kind of move temporarily. And now, before you note it, two things that normally do not have any type of charge separation now do have charge separation and a way to interact with one another. Once again, this is super temporary, super weak, because as soon as those electrons come back, they're going to be able to basically break apart that interaction. It's not going to hold, basically, very strongly in this case. The ability of somebody to do this is what is known as polarizability, and that is the ease at which electrons can kind of move around and create these temporary charges that occur. Now, the strength of a dispersion force is related to that. So it gets stronger with molar mass. That increases. So as the molar mass of a compound that is able to do dispersion forces is greater, the strength of that weak force becomes greater as well. So if you're comparing two dispersion forces, the one that has the greater molar mass will have the stronger dispersion force and weakest interaction. And that will mean that it should have the higher sort of boiling point and melting point versus another nonpolar molecule that has a lower molar mass. Any questions on that there?
Solid carbon dioxide, dry ice. Nonpolar molecules are arranged close to one another in a regular array where they move slightly around an average position. The distribution of electrons in a molecule can occasionally become asymmetrical, leading to the formation of a temporary separation of charges, a dipole. Partial changes on the molecule that form a temporary dipole then influence the electron clouds of nearby molecules. Although the dipoles are temporary, there is a significant attractive force between adjacent molecules as a result of the deformation of their electron clouds. These attractive forces are called London dispersion forces. London dispersion forces are the only type of intermolecular force found in nonpolar molecules.
So as I was talking about here, again, two nonpolar molecules, again, this kind of separation of electrons that happen here creates a temporary charge, and that then creates a temporary charge in the other guy, and now they do have a way to interact with each other, and again, going to kind of break apart. So when we talk about intermolecular forces, there's kind of three main ones that most people talk about. Again, we have hydrogen bonding, we have dipole-dipole, and we have dispersion forces. Now, in terms of strength, this is the strongest of all those intermolecular forces. This is the weakest. Again, as we talked about hydrogen bonding, in order for something to have the ability to hydrogen bond, it needs that special type of bond to be present, a bond between hydrogen and nitrogen, oxygen, and fluorine, one of those guys. And again, these are an example like water, obviously, here has the ability to do so. Dipole-dipole interaction, again, is also for polar molecules. And again, this is polar and polar molecules is the main force that can hydrogen bond. Dipole-dipole also between polar and polar molecules that cannot hydrogen bond. And again, example like we saw there, like CHF3. Again, having that ability to be polar, but cannot hydrogen bond is something that will be able to do that. Lastly, dispersion forces is your main type between nonpolar and nonpolar molecules. Again, everybody, even polar molecules, can dispersion bonds, but this is the main force for nonpolar. And again, we're something like, for example, bless you, CH4 and CH4 is an example of that. Again, has a bunch of hydrogens. None of them can hydrogen bond. It is a nonpolar molecule, and that is the main type of interaction that's happening there. Now, in terms of things like I mentioned before, things like melting points and boiling points, the hydrogen bonding would be the highest, and dispersion forces would be the lowest. Yeah. Again, though, if you're comparing kind of dispersion forces to dispersion forces, the strength increases with molar mass. So definitely something that's using dispersion forces will have a much lower melting point and boiling point than something that's using hydrogen bonding. But again, if you're comparing boiling points and melting points between two things that use dispersion forces, then the one again with the higher molar mass will have the stronger boiling point or larger boiling point and melting point. Now, these forces also affect things like solubility. These type of interactions affect things like solubility, and things that are soluble in each other use similar intermolecular forces. So things that have use similar intermolecular forces as whatever you're trying to mix it with, if they use kind of the same type of forces, then they're going to be very soluble in each other. If you mix two things that are using two different types of intermolecular forces, they're not going to mix or not going to be soluble. So intermolecular forces plays a big role in solubility. It also plays a really big role in things like melting points and boiling points. Any questions on any of that there? Yeah. Then let's talk a little about evaporation and vaporization now that I wrote all over this thing here. Let me get rid of that there. Just what I think. I'll do that. So evaporation and vapor pressure, as we talked about, evaporation or vaporization is the process as we go from liquid to gas. So going from the liquid phase to the gas phase, that is evaporation. Obviously, condensation is going in the other direction, going from gas back to liquid. The vapor pressure of a liquid is, or the pressure of the vapor above the liquid is what is known as the vapor pressure. Liquids with high vapor pressure are said to be volatile. They evaporate really easily. So when we talk about vapor pressure, we're talking about a liquid. And at the surface of the liquid, there is always going to be molecules jumping out of the liquid phase into the gas phase, and there's gas molecules dropping back into the liquid phase. They go back and forth. And what happens is with normal evaporation, you will get some gas molecules above the liquid. And because gas molecules create pressure, that is what is known as the vapor pressure here. And the higher the vapor pressure, the solution is volatile, which means it can go into the gas phase pretty easily. The only way that you could get a high vapor pressure is you got to have a lot of molecules jumping out of the liquid phase into the gas phase, basically. That occurs when you have things that are held together by very weak intermolecular forces, like dispersion forces. A lot of organic compounds are nonpolar and they're held together by dispersion forces, which are really weak. And if you think about kind of the early organic molecules, things like methane, propane, and butane, you may be familiar with those. Those are all like gases under normal conditions. And that's because they're held together by super weak forces that they're just going to kind of break apart and go off into the gas phase. That's also why if you get into organic or you take organic ever and you use organic compounds, oftentimes they put you in fume hoods because those organic compounds, even though they're in liquid phase, you open the bottle, they'll just jump into the gas phase and become a vapor very, very easily. And a lot of them are flammable when they do that, so they can catch on fire and stuff like that. So they oftentimes will put you in a fume hood for you to work in there to prevent that hopefully from happening. Now, when we talk about the vapor pressure of a liquid, again, the stronger the intermolecular forces, the lower the vapor pressure will have. So the stronger the intermolecular force, that's what it says on the bottom here, the weaker are the lower the vapor pressure will be. And again, because it has a really strong intermolecular force, what that's going to do is keep most of the molecules here in the liquid phase, and not a lot of them will escape out into the gas phase, and you'll have a lower vapor pressure because of that. Again, somebody with a weak intermolecular force will be allowed to kind of escape into the gas phase easily and create a much higher vapor pressure. Now, when we talk about a liquid in a container, there is something that occurs when you have a liquid in a closed container. What happens is at the surface of the liquid, you're going to start to get some evaporation occurring. and some of those liquid molecules are going to start to evaporate, and you're going to have a much greater rate of evaporation at the very beginning than you do condensation. So when these guys start to go, they got nowhere to go because the lid's on there. So what happens is we're going to get some guys coming back the other way and doing condensation and dropping back down into the liquid phase. Eventually, it'll come to equilibrium, which means the rate at which everybody leaves the liquid to make a gas will equal the rate at which those gas molecules basically come back into the liquid phase, and that's equilibrium. And if you look really closely at the volume in the closed container, you normally will see kind of a slight change in the volume. And that is because when we started, we had no gas molecules that have escaped. Obviously, some gas molecules escaped, increased some of the vapor pressure, and that means the only way to get those gas molecules is they had to leave the liquid portion. And we'll see just a slight little drop in the overall volume because now you have gas molecules above the liquid and you have some vapor pressure above that in this case. Any questions on that there? All right. So we're just talking just very briefly here about solids. There are a couple of types of what I refer to as crystalline solids. Two types. There's ionic solids, where ionic compounds come together. They come together in a very, very organized pattern, a long-range pattern of an ionic compound, kind of maximizing the positive cation and the negative anion attraction, intramolecular forces, and minimizing those other. There's also molecular solids like sucrose, and a third type, which is basically just atoms of one type of element, which is sometimes referred to as an atomic solid. Here's a picture of an ionic solid, and again, you can see it's a very ordered arrangement. It is so ordered that you could take just like a little snapshot of it, the pattern, and you can repeat basically the entire pattern and rebuild the entire molecule. It's so repeatable, sort of a very long range order that you have with it. And again, these are our three solids in this case. All right, I think that's it for solids and this chapter. So that will wrap up chapter 14, and we'll lay it up there for now, I think.